In today's news, NASA named an asteroid after the German physicist and science communicator Sabine Hossenfelder. This is not a joke. I got an email about 5 weeks ago from someone who said he works at NASA's Goddard Space Flight Center in the Small Body Group. At any other place, that'd be the local kindergarten, I guess. But at NASA, the Small Body Group is concerned with, well, asteroids, comets, and other small things that fly around in space, like, for example, my daughter's left shoe on Monday morning. So the NASA guy writes, they're about to name the next set of asteroids, and he wants to propose that one is named after me. Sabine Hossenfelder is unfortunately too long, as that's more than 16 characters. So what would I suggest, he asks. Just between you and I almost put this email into the bin. Had I not, on this very morning, seen a call from NASA on Twitter asking to submit new suggestions for asteroid names? Coincidence?
It was coincidence.
I looked up his IP address, and sure enough, it points to somewhere near Maryland. What did you have done? I replied to him and said, how about just Sabine? But it turns out there already is an asteroid by name Sabine. It was discovered in 1908 by a German living in Heidelberg. His name was Karl Wilhelm Lorenz. He died aged 32 from the Spanish flu. Very tragic. I imagine that Sabine was his girlfriend. In any case, I said to the NASA guy, just make it Hossi then, because that's what they called me in school, what with my long family name and all. And here we go. Now there's an asteroid called Hossi. It's in the main asteroid belt between Mars and Jupiter, about 500 million kilometers or so away from Earth. It's mostly rocky rather than icy, goes around the Sun about once every 3.5 years, and has a diameter between 3.5 and 6 kilometers. It was discovered in September 1993 by the Belgian astronomer Erik Elst, who died in 2022. Elst discovered more than 3,000 asteroids and didn't name this one. So now it's called Hossi, and I'm very proud of it. Unfortunately, no one's taken an image of my asteroid, so I made one myself. Here we go. I actually feel bad now, because I so rarely talk about asteroids. It's because on the occasions that I did talk about asteroids, no one really seemed to care. And yeah, I get it, because from one point of view, asteroids are just rocks floating around in space, and a rock is a rock is a rock. On the other hand, some of those rocks are more the size of mountains, and on occasion one of them falls down on us. Indeed, asteroid impacts are one of the biggest existential threats that our species faces. This is why NASA and some other space agencies are working on ways to identify asteroids that come our way early, figure out how large they are and what they're made of quickly, and try to find a way to redirect them in case that ever becomes necessary. I've been thrilled that NASA took on the challenge with the DART mission that they let crash into the asteroid Dimorphos in 2022. The European Space Agency contributes to this project with its own spacecraft Hera that's on the way to Dimorphos to figure out what effect the impact had. Hera is expected to arrive in 2026. Of all the scientific research that's being done on this entire planet, asteroids are without doubt one of the most important ones, and also one of the most underappreciated ones. Maybe they just shouldn't call them small bodies. That sounds kind of lame. Flying mountains, dinosaur killers, hunker-junks. But it's not just the dinosaur killing that makes small bodies interesting. They're also scientifically interesting. That's because they're really old, billions of years, and some of them quite possibly came from outside our solar system. Some scientists even think that life on Earth might have come from elsewhere, and if it did, then it probably came on some small body that hit Earth. Last but not least, asteroids are becoming commercially interesting. I know it sounds crazy to launch a spacecraft and fly millions of miles to dig on an asteroid rather than doing it here, but you have to keep in mind that A, mining is also expensive on Earth, and the less expensive space travel becomes, the more interesting asteroid mining gets. And B, you might not even want to bring the stuff back down to Earth. You could use asteroids as stepping stones for space travel. You can harvest resources there, including water that has been found frozen on many asteroids, and build your spacecraft there, or at least repower them. So yes, asteroids are rocks, but they're very interesting rocks. This will get a top entry on my list of bragging rights. Twin birth without cesarean, marathon in less than 4 hours, asteroid named after me. That definitely wasn't on my bingo card for 2024. Space potato, anyone? Clickbait is what people today call anything they don't like. Most of them, I think, have just forgotten what clickbait is. And this is why for today's news, I've made up some clickbait headlines. I can't believe this really worked. Nuclear precision, finally! Scientists don't want you to know this one trick for making nuclear clocks. They poked an atomic nucleus with a laser. You won't believe what happened next. So what happened next? Well, the nucleus started to wiggle, and my not very admirable task is now to try and explain why that's interesting. I think it is interesting because one day there might well be a Nobel Prize for it. Not an exaggeration, because it's a breakthrough similar to last year's Nobel Prize in Physics. Let me guess you can't remember what last year's Nobel was awarded for. Yes, to be fair, if I wasn't doing the science news, I'd probably have forgotten as well. It was for attosecond physics. An attosecond is a billionth of a second, or 10 to the minus 18 seconds. Just for context, that's even shorter than TikToks. The reason there was a Nobel Prize for it is that laser pulses, which are that short, have allowed physicists to study and manipulate the structures of molecules and their chemical properties. It doesn't sound particularly groundbreaking, but it's opened an entirely new range of applications. And I believe that the laser that poked a nucleus will open up an entirely new range of applications just like that. You see, everything has a typical resonance frequency. You know this from glasses and cars and bridges. Atoms have resonance frequencies too, or rather the electron shells which surround them do. These atomic resonance frequencies are extremely stable and robust under environmental noise. This is why you can use them to generate very precise clocks. You do this by tuning into these resonance frequencies of atoms, and that gives you a time standard. This is how atomic clocks work. It'd be even better to use atomic nuclei, because atomic nuclei are even less affected by their environment, and the resonances are even sharper. They could make for even more precise clocks. The problem is that for nuclei, these excitation energies are in the range of some mega electron volt. To access them, you'd need wavelengths in the X-ray range. And while I'd really like to have an X-ray laser in my phone, I'm afraid that isn't going to happen anytime soon. At the moment, X-ray lasers are big and bulky and really expensive. But here's the thing. Some atomic nuclei have several resonances that are very close together. And while each of them has a high energy, the energy you need to switch from one such resonance to another one nearby isn't all that high. If you could use one of those switches, you'd get nuclear precision without the high energy. And this is what they did in this new work. They used thorium-229, whose nucleus is known to have two close-by resonances. They embedded the thorium atoms into a crystal, and then they just had to hit exactly the right energy. That took quite some trial and error. Indeed, they've been trying this since the 1970s, but eventually they found it. Since you ask, it's at 148.3821 nanometers, which I guess the lead author now uses as his password. If you remember that visible light has wavelengths in the range of 400 to 700 nanometers, you can tell that it's just about in the ultraviolet. For nuclear physics, that's a very low frequency or low energy respectively. Why is this cool? Because this will set a new precision standard for time and with that also for distances. It's the beginning of a new era that'll in the long run make everything more precise, just like atomic clocks have made everything more precise. Not just our timekeeping, but also navigation, satellite measurements, maneuvering in space, and scientific experiments. And this is the beauty of scientific progress. It leads to new technologies, which lead to better experiments, which lead to new insights, which lead to more progress. In principle, in practice, I just want the headphone jack back. It might seem like we're surrounded by constant progress, better cars, faster phones, virtual reality, the Internet of Things that we're told is just around the corner. Though it's been there for so long now, I wonder what it's doing behind that corner. Things notwithstanding, it certainly looks like progress. Drones, VR glasses, Alzheimer drugs, robots on the moon. Amazing! And yet, how new is all this really? Is a foldable phone a breakthrough invention? Is gradually cramming more and more pixels and transistors into headsets a sign of progress? Aren't machines on the moon more of an engineering feat than a scientific revelation? Is this the end of science? I've talked about this a few times previously, and I do think science is in big trouble indeed. But last week I read a press release saying research has lost none of its innovative drive. And well, that doesn't agree at all with what I said. So I've had a look. Before we get to the new paper, here's the background. The number of scientists in the world is higher now than ever before. It's not just overall population increase, the fraction of people in research and development itself is increasing. Globally, it went from about 1 in 1,000 to more like 1.5 in 1,000 in the past 20 years. But in most of the developed world, the numbers are much higher than the global average. For example, in Germany, more than 5 in 1,000 people now work in research and development. Those damned scientists are everywhere now, even on YouTube. And more scientists means more papers. We now see more than 5 million new scientific articles per year and about 3.5 million new patents per year. But it's not so surprising that more people means more papers, is it? Indeed, in 2020, two researchers from ETH Zurich said that all this paper production is covering up what's really going on. That is a steep decline in research productivity. They counted the number of top researchers, those which have made major contributions to a field of research, because these people are usually not hard to identify. They then assign the top researchers to their active research years. This way, they avoid having to count discoveries. It's quite clever, really. You can see in this figure, for example, the number of top researchers during the first revolution in quantum mechanics. Then they normalize this by the total number of researchers, and this is what they call research productivity. With this measure, they find that the research productivity has steeply decreased since the 1960s and 70s. From the way that they've defined it, this means that of all the scientists alive, fewer and fewer are contributing to key discoveries. This echoes an earlier argument by Patrick Collison and Michael Neilson, who pointed out that Nobel Prizes are increasingly awarded to work that was done long ago and that didn't used to be the case. Then last year a paper appeared in Nature which supported the earlier findings. The authors said that the number of disruptive ideas has noticeably gone down in many areas of science, including the physical sciences, chemistry, computer science and biomedicine. They looked at 45 million papers stretching back to 1945, as well as 3.9 million patents, and at how often those papers and patents were cited. Then they measured whether a new paper or patent made citations to earlier work redundant, which they say is a sign of a disruptive breakthrough. Using this metric, they found clear evidence that both papers and patents have become less disruptive over time in all areas that they looked at, even in the top journals such as Nature and Science. The team says that this shows a fundamental shift in the nature of scientific inquiry. Scientists are making fewer and fewer breakthrough discoveries and instead work out the details of the knowledge that we already have. Now about the new paper with the press release that said research is doing just fine. This was actually a reply to the paper from last year that I just talked about. The authors of the new paper say that the analysis in that earlier paper was just wrong because they excluded citations to patents published prior to 1976. This had the effect that many patents published in the late 70s and 80s would appear groundbreaking simply because the references to earlier works were missing. Since the groundbreakingness of the 70s and 80s was overestimated, this made the later years look worse. It's kind of like everyone thinks the time they've grown up in was the best because they've no idea how miserable people were before their birth. Well, so the authors of the new paper corrected the mistake in the earlier paper, but that didn't make the decline of disruptiveness go away. The disruptiveness of patents still drops, just not as much. And it didn't change anything about the conclusion that research papers have become less disruptive. So basically, the title of the press release is nonsense. All these analyses draw the same picture. Scientific progress is declining. And why is that? There are three major hypotheses. The first is the one that most scientists prefer: deny that a problem exists and insist everything is going just fine. The second is that there's just nothing left to discover. This is the death rattle of science and the disease is fatal. The third is that the current way of organizing scientific research impedes progress by rewarding productivity over usefulness. Personally, I think it's all my fault because I still haven't found a way to make cold fusion work. Every time I talk about particle physics, I get complaints. When I say this stuff is nonsense, people complain it's not nonsense. When I say it's not nonsense, people complain it's nonsense. But today's news is different. It's both nonsense and not nonsense at the same time, so everyone will have something to complain about. It'll be glorious. Let's have a look. This news is about a test that particle physicists have done with data from the Large Hadron Collider. They wanted to know whether the particles in their collisions play by the rules of quantum physics, whether they have quantum entanglement. Entanglement is a correlation between quantum particles that can be stronger than any correlation you can get without quantum effects. It's the smoking pun of quantum physics, so to speak. This test is nonsense because we have tested this thousands of times before. There was even a Nobel Prize for confirming that, yes, entanglement is real. And of course, you already know that the new test confirmed quantum physics, because otherwise Fox News would have declared all of physics wrong. And yet, it's not nonsense, because none of these other experiments were done at such high energies as the Large Hadron Collider reaches, and doing the test at such high energies could reveal the origin of the randomness of quantum mechanics. That wasn't my idea, unfortunately. It came from Gerard 't Hooft. He was awarded the Nobel Prize in Physics in 1999, together with Martinus Wertmann, for his contributions to the development of the Standard Model. But before I tell you what he's been going on about for a few decades now, let me tell you what they did at CERN. The ATLAS collaboration at CERN tested quantum entanglement with pairs of particles, a top quark and an anti-top quark that can be created in proton collisions if the energy is high enough. Quarks have a spin, and what you want to know is how strongly the spin of the top quark is correlated with its anti-top partner. The top quarks are good candidates because they're heavy and short-lived. And since they're short-lived, there isn't enough time for the correlations to be washed out. The correlations get passed onto the particles that the top quarks decay into. They catch these decay products in the detectors and calculate what the spin must have been. They reconstruct the spin values of the original particles and quantify their correlation in a number they call d. If d is smaller than -1/3, then you have true quantum entanglement. And as you can see here, that's what they find indeed. All works as expected. Now, one way you can look at this result is that it's nothing new, boring. But I look at it as a test of an idea that's so underappreciated you've probably never heard of it. It's the idea from Gerard 't Hooft, who I mentioned earlier. He thinks that the randomness of quantum mechanics that we observe in the laboratory has an explanation. It comes from information that's hidden on very short distances in the so-called hidden variables. In tabletop experiments like those typically done for testing quantum physics, you can't see what's going on at very short distances. For that you need a big collider. That's why they built them, because high energies test short distances. No, it's not just because they like really big and expensive machines. At least I don't think so. Somewhat ironically, particle physicists themselves tend to be not excited about testing the foundations of quantum physics. Most of them probably think what 't Hooft says is crazy. This is because of how their current theories work. They always assume that what happens on short distances is not relevant for what happens on longer distances. It's called the decoupling of scales. But a key feature of chaotic systems is that what happens on short distances doesn't stay on short distances, what with the butterfly effect and all. So I'm totally with 't Hooft. Just because we haven't found an origin of quantum randomness in tabletop experiments at low energies doesn't mean we won't find one at high energies. And yes, that'd be an example of what's called a superdeterministic theory. Now, let me be clear. It's not that 't Hooft is saying you can see evidence for that at the Large Hadron Collider. It's that generally, if you look at shorter distances, you have better chances to find those hidden variables. That's why I think this test is not nonsense. To the contrary, it's one of the things that keeps me up at night, that the guys at CERN are sitting on a breakthrough discovery in the data, but they don't know it because they haven't run the right data analysis. Or worse, they might actually have thrown the data away. The other thing that keeps me up at night is the squeaky hinge on our fireplace cover. But let me say a little bit more about Gerard 't Hooft's idea, because I'm afraid basically no one takes him seriously, and I understand why. His idea belongs to the realm of quantum foundations, but 't Hooft isn't a quantum foundations person. He's a particle physicist. He doesn't speak the right language. So the quantum foundations people don't get it. And the particle physicists don't get it either, because they don't think quantum foundations matters. So no one cares. And this, ladies and gentlemen, is one of the reasons I'm here on YouTube telling you about this, to draw attention to ideas I think haven't received the attention they deserve. No, I made this up. I'm just here to make jokes about particle physicists. This is news that I certainly didn't see coming. Do you remember Roger Penrose's idea that the human brain uses quantum effects in microtubules, and that those are the origin of consciousness? Yeah, that sounds pretty crazy. But, well, it seems that he was right, at least about the microtubules. What the heck are microtubules? Microtubules are big molecules, basically. They are essential parts of all cells in the human body and play a big role for signal transport in the human brain. They're polymers that combine two tubes and are made of smaller components called tubulin. So the tubes are made of tubules that are made of tubulin. It's tubes all the way down, people. Roger Penrose now has this idea that consciousness can't be explained by a computable process. So there needs to be an uncomputable element in what the brain does, and that, he says, can only be the collapse of the wave function in quantum mechanics. The collapse is when a quantum distribution of possibilities collapses to one actuality. His hypothesis is that this happens in the human brain, and that's what creates conscious thought. Why the collapse of the wave function? Because we know that all the rest is computable, so that's the only place you can hide something non-computable. The problem with this idea, as many physicists have pointed out, is that the human brain is a warm and noisy place, and these are generally not very welcoming to quantum physics. There's a reason that current-day quantum computers are suspended from 3 levels of shock absorbers and cooled to a few millikelvin. It's not just because it looks impressive, though there's that. It's because otherwise the quantum effects just go away too quickly to do any computing with them. For Penrose's idea to make any sense, you'd have to have quantum effects survive in the human brain at least until a neuron has managed to fire. And the human brain is ridiculously slow in its firing. Even the most basic estimates say that it wouldn't work out. Penrose originally didn't say anything about specifically how these quantum effects should come about in the human brain, but he later teamed up with Stuart Hameroff, a neurobiologist who had this idea that it'd be the microtubules. The microtubules, Hameroff convinced Penrose, can basically synchronize due to quantum effects, and that helps the quantum effect survive for long enough to play a role in conscious thought. That still doesn't explain what any of this has to do with consciousness, but at least that'd make it plausible that the collapse of the wave function plays any role in the human brain. I've heard more than one person say, what a pity that Penrose fell for this crazy Hameroff person. But well, I've met both Penrose and Hameroff, and they're both crazy, of course, but neither of them is stupid. So what are we to make of this microtubule business? Now comes this new paper from a group that doesn't seem to have anything to do with either Penrose or Hameroff, and they say that they have clear evidence that these microtubules actually do display real quantum effects. More specifically, it's a process called superradiance. It basically requires the molecules to have quantum links to each other to achieve a larger emission of light. They first built a computer model for how the tubulin molecules combine to microtubules and how they would absorb light. Then they also tested this in the laboratory, and they found good agreement. Both theoretically and experimentally, they say that yes, these tubules can display quantum effects. They didn't actually test it in a cell, just in a solution, but it's at room temperature, and they say the superradiant effect basically doesn't care about the environmental noise. This is very interesting, just because it's an example for quantum-enhanced effect that seems to be unexpectedly robust. I'd be surprised if not the quantum computing people will try to use it. Another interesting part of the paper is that they say that the quantum effects in these microtubules can do something else, which is that they become much more efficient at absorbing ultraviolet light and redistributing it to lower energies. That is, they basically protect cells from the potential harm of ultraviolet light. In the press release, the researchers say if these quantum effects fail, that might play a role for degenerative brain diseases. I'm somewhat skeptical about this, but then this isn't my research area. What does any of this have to do with consciousness? Nothing really, though last time I looked we did need brain cells for consciousness. There seems to be a big logical gap between there are quantum effects in human brains and quantum effects create consciousness. Though, come to think of it, maybe the time has come for a quantum consciousness startup. Thanks for watching, see you tomorrow.